Okay, welcome to one of the last lecture of Advanced Applied Econometrics this semester. It's actually my last lecture, right? Today, we first talk about the standard Tobit or Tobit-2 in physics notation. And then later on, I will also give you a brief overview of some other alternative for sensor variable models. And first, let's talk about the motivation of the standard Tobit. Like we said briefly in the previous live session, the standard Tobit or Tobit-1 is rather restrictive in the sense that the very same set of explanatory variables explain the probability of a zero, or you could also say the probability of a non-zero observation, because those two just counterparts of one another, right? And then later, it will also appear in the part to explain the level of the non-zero variable. You can see this in the log likelihood or the likelihood function. And then, moreover, if you look at the marginal effect of the variables on these two parts, if you derive now the marginal effect of certain variables on the probability, and then derive the marginal effect of the variable on the expectation of the non-zero variable, you will see that they have the same sign. And this is restrictive because it does not always fit into the reality. One example I told you last time with household expenditure for vacation. Another thing you could think about is, I took this example from a textbook, the tobacco consumption and advertisement. So it has been shown by several studies that advertisement has some positive effect on the probability of smoking. So whether a person decide to be a smoker or not depends are related to the advertisement. Okay. However, later on, once the person becomes a smoker already, advertisement will have minimal or no significant impact on the extent to which he or she smoked, how much. And another example, probably not so economic in a sense, is the probability and the damage of fire for old versus new building. So old building are easier to get fired. However, if the fire occurs, then new building will likely to have more damage. Why? Because new building tends to be more valuable than old building. So in such cases, using the same set of explanatory variables will not fit quite well to the reality. And there we have Tobit-2, or also called the sample selection model, to deal with such situation. Okay, despite the fact that we talk a lot about wages in different contexts this semester, let's again have another wage model, because this is the most illustrative and also the most classical example for Tobit-2 model. Now suppose we want to explain the wage of certain individuals using the linear function of a set of characteristics. So here you have a linear function again with wi start being the wage of individual I. And then you explain by the set of characteristics collected in x1i prime could be, for example, gender, education, age, marriage status, experience, all sort of thing we talk about a lot, right? And this functions linear, very familiar. And of course, we also have a stochastic component in epsilon 1i that collects all the unobservable characteristic or unobservable heterogeneity of the individual. So these things together explain the wage level, okay? However, we could imagine that we only observe wage for those people who are working, right? So you could interview people, give them a survey. So only those who are actually working will fill in a number in the wage data. Otherwise, that will be 0. So up to here, it's going the same direction as the Tobit-1 model, right? This thing we know already. However, what makes it different now is we allow for the probability of working or not to be explained by a second equation, which is different from the first one. Different in the sense that we have a different set of explanatory variables, x2i prime here, now, to distinguish it with x1i prime up there. And then we also have a second stochastic component, the second error term with all unobservable characteristic of the person, which determines if he or she works or does not work. Okay, so the idea here, the setup here, just to tell you that now, in order to overcome the limitation of the Tobit-1, we allow for the two process. This is, we could see it later, intensity. And here is participation, to be determined differently. So there's two processes in there. Therefore, we would have slightly different observation rule, as you will see on the next slide. Now let's take it slowly, step by step. So we've seen on the last slide that hi star 0 is now the latent variable to determine whether the person will work or not, right? So if hi star larger than 0, then hi would be 1. Well, technically, will you observe this 1 from your survey data or your data set? Well, not really, because you may observe or you may record it only the wage, the actual wage, or if don't have wage, then 0, right? But you've seen that in the assignment already that we could actually construct this indicator, the binary indicator, hi, equal 1, and then you observe some wage, and this wage equal the latent, the half or the partly latent wage, yi star. On the other hand, if hi star equals 0 or negative, then you don't observe wage. Therefore, you know that hi equals 0 and the wage not observed at all, right? So that is the idea. Back to here, with the two error terms, usually it's assumed to be biverge, normally distributed now, and therefore they have a covariance matrix now with the main diagonal being the variance of the two error terms, right? And the other two are the covariance, okay? That we know already. However, because here the second equation is a standard probit model, the binary process, right? Hi equal 1 or 0. Therefore, we will have to normalize the variance. And usually the easiest way we set sigma square 2 equal to 1. Because we don't observe the scale of this hi star variable at all. So we have to normalize the variance of the error of this equation. Okay. So again, back here, this part is the intensitive part, right? And this part is the participation part. And the two driven by two different set of explanatory variables, as we have seen. And then now we go from there. So this is just to repeat what I have stressed earlier, that the thing that really make a difference here is that we allow for x2i prime to be different from x1i prime and beta1 different from beta2. If we set these two guys equal and then the two error terms equal, then we go back to the Tobit-1 model again. So the main point here is we allow for participation and intensity to be modeled or to be explained differently by different variables and characteristic and unobserved endogeneity of the observation. Okay, so let's do some derivation. I know you don't like it, but I don't know how else we could understand what is the way it's on slide 10. So let's go through it. So the first thing we know is that the two different decisions in this case, the two process, the wage and the decision to work, governed by two different processes with different set of explanatory variables. They may or may not overlap, we'll see later. And then we have the two error terms biphasically normally distributed with mean zero and the covariance variance matrix given by this. This information will be important for the derivation. But first, let's write down the notation of the conditional expectation of wage, WI, conditional on what? On having the person working. So HI equal 1. What we interested in. The first thing to realize is it actually equal the expectation of WYI star conditional on HI equal 1, right? Because when HI equal 1, meaning the person working, you observe part of this latent process of wait, which is the same as WI, that we have set out in the beginning, right? And that would be because we WI start here equal x1 I prime beta 1 plus epsilon 1i, we just plug it in over here, right? x1 I prime beta 1 plus epsilon 1i conditional on hi equal 1. All right, that's the first thing. Very good. Then we'll move further. Now the next thing to realize is this x1 I prime beta is deterministic as ever, right, with the linear model. Therefore, when you take the expectation, you can just pull it out of the expectation sign. So x1 I prime beta plus inside the expectation we only have epsilon 1 I prime conditional on hi equal 1. And this is the first line on your slide. 10. Alright, let's move further. The next step, we know that hi equal 1, meaning these latent variables that govern the decision to work, hi star is positive, right? Meaning the part on the right hand side of the equation is positive x2i prime beta 2 plus epsilon 2i is positive, right? Meaning epsilon 2i larger than xi minus, x2i prime beta 2. This now we should be familiar already. Therefore, we plug it back into this first line, we would have the expected value of the conditional expected value of wage, conditional at I equal 1, just the thing in the beginning, equals, so now x 1i prime beta plus the conditional expectation of epsilon 1i prime conditional on epsilon 2i, no, epsilon should not be have prime over here, no, larger than minus x2i prime beta 2, right? And this is the second line on your slide. Okay, all right, let's move further. We also have for two random variable x and y. So now x and y is nothing related to our, right? I changed the color easier. This is from Fairwick Appendix B6. Now, we have, so the thing is now we have to sort this out. Now, the conditional expectation of x upon, let's say y, upon x larger or equal to a certain value c would be the expected value of y, plus the covariance of the two random variables, here yx divided by the variance of x, and then time inside the bracket the conditional expectation of x itself, conditional on is larger or equal to a certain thing. And this is what? This is the truncated expectation that we have seen in the binary choice. No, Tobit-1, but we'll go back to that later, okay? Now, minus the unconditional expectation of x itself. Okay? Because that pen doesn't work. Change the color. So set y equal, so y and x in here, we plug it back to epsilon 1i in our model, and then x is epsilon 2i mu y equals to mu epsilon 1, mu x equal to mu epsilon 2. How large is that? We need the information over here later. No. Then sigma yx or xy, which is the same, equal sigma 1, 2, and sigma square 2 equal sigma, x over here. Then we could go back to our equation 2 over there, but we could write the expectation, the conditional expectation of epsilon 1i, conditional on epsilon 2i larger or equal to minus x 2i prime beta 2, right? Here also CA minus xi 2i prime beta 2 equal the mu y, which is 0, right? Because it's mu of the mean of epsilon 1i, 0, right? Plus sigma 1, 2, right? Divided by sigma 2 square, times inside the expectation of x is epsilon 2i, right? Conditional on itself larger or equal to minus x 2i prime beta. Okay? Minus mu x. You may not see this clearly. Mu x is means of epsilon 2i, again 0, the unconditional mean, right? So therefore this part will be down to sigma 1, 2, and sigma 2 square over here we have 1, so just 1, right? We don't have to rewrite it, times the expectation of epsilon 2i conditional on itself larger than minus x 2i prime beta. You could drop the equal sign over here, it's fine. Okay. And this is what appears on your third line. I could rewrite it again. So 2, because we have 2 over here, equivalent to, again, the conditional expected way, conditional on hi equal 1, equal, we still have x 1 I prime beta 1. I missed this part, beta 1, okay, without I think there, plus sigma 1, 2 times the expected value of epsilon 2i conditional on itself larger than minus x 2i prime beta. And this is the third slide. Sorry, line, not slide. Okay, I go back after cleaning the board and we could finish that. Okay, last step. So, if you remember, last lecture, we've seen that already. What is that? Well, this should be third. This is the expectation of truncated normal distribution, right? And we have a formula for it. We have the expectation of a truncated normal distribution of epsilon to I truncated at the point minus x to I prime beta 2 equal to the ratio of the value of the probability density function, which is small phi now, of x to I prime beta 2. Why we have the phi now? Because we normalize, sorry, not normalize, but we standardize the distribution of the second order term to have variance of 1. So it's a normal standard distribution. Yeah? So that's why it's the phi. And in the denominator, we have the large phi, which is the cumulative probability at the same point, xi prime, x2i prime, beta 2. Okay? Therefore, again, we could plug it in 3. And to have the conditional expectation of wage, conditional on the person working, given by, again, xi, x1i prime beta 1 plus sigma 1, 2 times this term, right? Small phi of x2i prime beta 2 divided by large phi of xi prime, x2i prime beta 2 again. And this is what the final result given on your slide 10. Here, okay? Why it is the way it is. So now several things to notice. Actually, only two main things. The first point is if sigma 1, 2 equals 0, meaning these two are terms uncorrelated, what happens? The whole thing here will be 0, right? The whole part over here will be 0. And the conditional wage down to x1 I prime beta 1, a linear function. You could again simply use OS and ignore this part to estimate that. However, even in that case, you have to keep in mind that you estimating the wage, the expectation of wage conditional up on those observations. Those observations that actually participated in the labor market, the job market. Now, and because our sample includes only those people when the sigma 2 is 1, 2 is larger than 0, their expectation is larger. And their expected error of the first, the unobserved heterogeneity, also very likely not to be 0, the expected value. Okay, that is use OLS to estimate expectation of wage conditional on h equal 1, yi, and this part, okay? But remember, that's you only estimate the expected value of wage for a subsample, a subpopulation, okay? That's the first thing. The second thing, we have the ratio lambda equal to the x to I prime beta and below the large phi of x I2 prime beta. These are called the inverse mu ratio or Heckman lambda, named after the person Heckman, the one who proposed to use it. How do you understand that? You could think about this ratio as the amount of truncation, the amount of truncation for this distribution of epsilon to I. How large is the proportion of the people who's not working that we could not absorb? The larger the lambda is, the larger this part, this amount of truncation is. So meaning the thing that we observe here is only a small part of the larger population or the larger sample. Okay? There another thing, even though here I said about sigma 1, 2 equals 0, in reality there's reason to expect that they're different. It is different from 0. We will see in the next slide. Okay, to understand why we should expect the covariance between the two atoms different from 0, like I just said, let's go one step further and put some more assumption. So the idea here is to look at it from an even more economic perspective, okay? Now let's think about it. Assume that as a person, we will work if the wage that we offer larger than some reservation wage, or the wage that we somehow expected that we should receive now. So this reservation wage is denoted as WIR. This reservation wage, as you could imagine, will depend on all sorts of personal characteristics, so that we could write it as a linear function of some vector z, zi. Here's some vector of personal characteristic, and of course there's some unmeasurable or unobservable component over there. Okay. Now, in turn, the wage that we are offered when we, for example, go to the job market will also depend on individual characteristic. This characteristic may or may not overlap with Z, but again, as you could imagine, there will be some overlap over there. For example, age, education, and the experience. Such things will enter both equations. And the offer wage here is again the WI star that we talked about before, the partly like latent variable. Okay, so this equation is familiar to us with the atom epsilon 1i. Then putting it this way, we will see that if WI star is lower than WRI, then the person will not work, right? Because what you actually get below your expectation, so to say. Therefore, now we have a slightly different observation rule where we have HI equal 1, meaning the person worked, you observe some wage, if the offer wage minus the reservation wage larger than 0. So the difference of what you expect, the difference of what you offer and what you expect is positive. Otherwise, it will be 0. So far, so good. Now, if we plug the two equations for the offer wage and the reservation wage that we have seen on previous slide in this latent variable to capture the decision of participation, then we have x1i beta 1 minus zi gamma, and plus the difference of the two atoms here now. And then if you define x1i beta 1 minus di gamma as x2i beta 2, and the difference of the two error terms as epsilon 2i. It will return again to the Tobit-2 model, right? Because this is the equation of participation that we've seen before. But writing the equation in this way help us to realize also two things. Epsilon y1i and epsilon 2i is correlated. Why? Because epsilon 2i equal epsilon 1i minus, unfortunately, I've forgotten how to call this Greek letter. Perhaps you could help me tomorrow. Okay, so it's a function of epsilon 1i, and therefore we should expect that the two correlated, right? And the second thing is we have x2i prime would be x1i prime and minus zi prime, right? So even though there's the minus over there, you could understand that when we talk about x2i, we implicitly include zi over there and x1i. So all the explanatory variables that explain the alpha wage actually included in the explanatory variables that capture the decision to participate, right? So you could imagine, of course, whether you work or not depends on how much you offer. If you pay too low, then you rather not to work, right? Because it's not worth it. And right there already, you can see that all the characteristics that determine the offer wage is somehow taken into consideration for the decision to participate or not participate in the job market, right? So having gone through those theoretical model of wage, now we could just substitute the WI that we talked on previous slides with the YI, and we have a Tobit-2 model. So nothing really changed compared to the first time we saw this assumption, just substitute YI for WI. Coming to the estimation, let's first look at the log likelihood function of the Tobit-2 model. It's similar to the Tobit-1 model in the sense that the log likelihood function consists of two parts as well. The first part is observing either 1 or 0. We also had that in the Tobit-1 model, remember? And the second part is the distribution of yi given that hi larger than 0. So put everything together in a likelihood function in tech log, we would arrive in this form of function. So that this is the first part, the probability of observing hi equal to 0. And the second part, for those hi larger than 0, meaning hi equal 1, we have the conditional density of yi, the wage in previous example, for example, conditional on hi equal to 1, plus the log of the probability that hi equal to 1. All right. However, what is different here? The different thing here is now we see the yi and the hi's implicitly in the background explained by different set of explanatory variables, right? x1i and x2i over there. Because of this, it's rather complicated to derive this density, conditional density of FYI contingent on HI equals 0. We use the Bayes rule to arrive in this. So rather, we have the conditional density of Yi upon Hi equals 0 times the probability that Hi equals 1 will be equivalent or identical to the probability that Hi is 1 conditional on Yi times the density of Yi. And substituted in here, we have officially the form of the log-likelihood function of the Tobit-2 model. And the rest just substitute back what we have seen earlier with the probability of observing Hi equals 0 being 1 minus the normal, standard normal cumulative probability at the point x prime 2I times beta 2, right? This should be clear now. FYI, we know already, just follow a normal distribution, plug the form of the density function of normal distribution in here. And then we also have the last part looks a bit complicated, but it's actually the conditional probability of observing the person working given the wage. Okay. Well, even when we have the full log-likelihood function like that, very often the Tobit-2 model is estimated in 2 steps because it's more intuitive, simpler, and also it can provide the good starting value for the log-likelihood maximization later. So the first step, we will estimate the probit, the selection equation to get beta 2. Then having beta 2, it's possible to calculate this one, the lambda, the Heckman's lambda. And then you use it as an extra explanatory variable for the second step with this outcome or intensity equation. Rather quite straightforward, and we will look at it in an R example. However, again, just like the Tobit-1 or like a normal OS regression, linear regression, we will need to correct for heteroscedastic error if we want to do hypothesis testing. So that is for the Tobit-2 model. We will see an example during the live session tomorrow.